Hello students, good morning. You are welcome in the lecture number 16 of a chapter of chemical thermodynamics. In the last lecture, we have started with spontaneous processes, and we have seen that spontaneous processes are the processes which are taking place on their own accord without taking the help of external agency. They are naturally occurring processes. They are taking place in only one direction and they are irreversible in nature. There certain examples we have studied, like neutralization of NaOH by HCl, then transfer of heat from hot end to the cold end, rolling of ball from higher level to lower level, and flow of water from higher level to lower level are certain examples of spontaneous processes where they have tendency to lead to the state of equilibrium. All those processes are taking place with decrease in energy. At start, it has higher content of energy, and at equilibrium, there is a lower content of energy. Therefore, those processes are exothermic processes. But we have studied the criteria of only exothermicity is not sufficient in order to explain the spontaneous nature, because one example we have studied, ice, whenever kept open to the atmosphere, it absorbs heat and converted to liquid water. Solid ice converted to liquid water by absorption of heat, so that is endothermic change, and still that is a spontaneous change. So why that is spontaneous? Even though that is endothermic process can be explained with the help of second criteria, that is entropy. We have seen the concept of entropy. What is entropy? Entropy is measure of disorder present in the system, measure of randomness present in the system. So there we have studied, whenever solid is converted to liquid, disorder increases. Therefore, conversion of ice to liquid water is spontaneous, because disorder increases means entropy change is positive. The processes to which entropy change is positive are considered as spontaneous processes. Then in that spontaneous processes, with the help of entropy change, we have seen certain examples like breaking of calcium carbonate to calcium oxide and CO2 gas is also positive entropy change process and spontaneous. Conversion of iodine solid to the iodine gas whenever placed open to the atmosphere is also the process where positive change in entropy takes place. So that is also spontaneous. Whenever molecule is converted to atoms, measure of disorder increases, measure of randomness increases, entropy of the system goes on increasing, and therefore that is the spontaneous process. But we can explain the concept of entropy whenever the change in state is given. Solid converted to liquid, we know entropy change is positive. Liquid to gas, entropy change is positive. Gas to liquid, entropy change is negative. liquid to solid, entropy change is negative. So in the processes, we can easily come to know what is entropy change. Whether the entropy change is positive or negative, that we will easily come to know whenever a change in state in the chemical reaction is known. But had it been the case that there is no change in state, at that time also it is necessary to explain the entropy. Therefore, we have to study the quantitative definition of entropy. So let us see quantitative definition of entropy. Let us consider Q reversible is heat transferred to the system in a reversible manner, and T is absolute temperature at which heat is transferred to a system in reversible manner. The ratio of Q reversible upon T is known as change in entropy. So entropy change is nothing but a ratio of heat transferred to a system in reversible manner to the temperature. Now here, change in entropy is directly proportional to Q, but inversely proportional to T, reciprocal of T. Now let us see how it is there. Delta S is directly proportional to Q, because whenever heat is transferred to the system, we know that when heat is absorbed by the system, at that time what happens? Molecular motions will increase. Molecules by absorption of heat go quite away from each other. Molecular distances increases. Therefore, molecular motions will increase. And molecular motions is nothing but randomness that is responsible to increase the disorder in the system. So whenever heat is transferred to a system in reversible manner, molecular motions increases. Therefore, entropy of the system also increases. Therefore, delta S is directly proportional to Q in reversible manner. But if the heat is supplied, transferred to a system at high temperature, the increase in disorder is less. Whenever heat is transferred to a system at higher temperature, at that time the increase in disorder is quite less. On the other hand, if heat is transferred to a system at low temperature, at that time increase in disorder in the system is more. So higher temperature, less disorder. Less temperature, higher disorder is there. Therefore, it is considered that the change in entropy is inversely proportional to temperature and directly proportional to heat supplied, heat transferred to a system in reversible manner. So that is there about the quantitative definition of entropy. And in the last lecture, we have studied that whenever change in entropy is positive, the reactions are spontaneous. If the change in entropy is negative, the reaction is non-spontaneous. And if change in entropy is equal to 0, the process is at equilibrium. And there I have told you one example of this reaction: hydrogen gas plus half O2 gas giving H2O liquid. For this reaction, what happened to value of delta S? Is it positive or negative? It is negative. Why? because gas is converted to liquid. Gas molecules are continuously present in a random motion. Randomly they are moving. Disorder is maximum in the gases as compared with the liquids. Liquids are having less disorder, less randomness as compared with the gases. Therefore, liquids are having less entropy and gases are having more entropy. So here for this reaction, when your 1 mole of hydrogen gas react with half mole of the oxygen gas, giving H2O liquid, gas is converted to liquid, entropy change is negative and the value is minus 327. So this reaction should be non-spontaneous. As per our concept, this reaction must be non-spontaneous, but this is also a spontaneous reaction. 1 mole of hydrogen react with half mole of oxygen, forming H2O liquid with delta S minus 327 should be 327 joule per degree Kelvin. This reaction should be non-spontaneous. It should be non-naturally occurring process. It should be non-naturally occurring chemical reaction. But this is also a naturally occurring chemical reaction. This is also a spontaneous chemical reaction. Why this is a spontaneous chemical reaction has given the explanation over there on the basis of second law of thermodynamics. So see here, what is the second law of thermodynamics? We have seen the first law of thermodynamics and now here it is the second law of thermodynamics. This reaction is spontaneous according to second law of thermodynamics. It has stated that the total entropy change is positive during a spontaneous chemical reaction. Whenever a spontaneous chemical reaction takes place, entropy change continuously increases. Entropy of a spontaneous process continuously increases. It means that the summation of total entropy is always positive. For that purpose, delta S total is considered as a delta S of system plus delta S of surrounding. And according to second law of thermodynamics, it is stated that entropy change during a spontaneous process continuously goes on increasing. So even though delta S for this system is minus 327, this is the system. For this system, what is the value of delta S of system? Minus 327. But delta S of surrounding is positive with a higher value as compared with delta S of system. Since this is positive with higher value than delta S of system, therefore the total answer comes to be positive. How delta S of surrounding is positive? See here, this is the reaction with negative change in entropy minus 327, and for this reaction change in enthalpy delta H is minus 572 kilojoule per mole. This is the value of delta H, minus 572 kilojoule per mole. From this value we can calculate delta S of the surrounding. Delta S of system is positive. We must have a positive value of delta S of system, then and then only the process is spontaneous. Therefore that of the surrounding is considered to be negative. So for surrounding, this sign should be negative, and delta S of surrounding will be equal to minus Q reversible upon T. So it is minus again minus 572 into 10 raised to 3 joule. I have taken it in the joule. This is kilojoule. In joule, this will become minus 572 into 10 raised to 3 joule per mole. So this value I have taken in joule because this is in the joule. So minus, this is also minus, divided by temperature, standard temperature to 198. Minus minus become plus 572 divided by 298, and this comes equal to 1919 joule per mole. Log of numerator minus log of denominator and then antilog. Log of numerator minus log of denominator and then antilog. This answer comes to be equal to 1919 joule per mole. Substituting over here, so delta S total will be equal to delta S of 16 minus 327, that of the surrounding plus 1919. Therefore, this answer comes to be equal to 9 minus 7 2. Then 11 minus 2 9, then 9 minus this 4 5, and then 1. So it is 1592 joule per mole. 1592 joule per degree Kelvin per mole. Joule per degree Kelvin per mole. This is the value, joule per degree Kelvin per mole. Since this is positive, even though here delta S looks to be negative, but this process is spontaneous. Therefore, delta S total is considered. According to second law of thermodynamics, entropy change is always positive during a spontaneous process, and the total entropy change is considered. The summation of entropy of system and surrounding comes to be positive. Therefore, these type of processes are spontaneous. So, what is the criteria we have studied on the basis of entropy change? If delta S total is positive, means greater than 0, the reaction is spontaneous. If delta S total is negative, means less than 0, the process is non-spontaneous. And if delta S is equal to 0, the process is stopped. It is the process at equilibrium. But over here, we have seen the second law of thermodynamics, where delta S total is considered, and that is the summation of delta S of system and surrounding. But we are more interested in the value of delta S of system and not surrounding. We are interested in the value of delta S of system and not surrounding, or rather, it is highly difficult to calculate the value of delta S of surrounding. Therefore, it is necessary to explain the spontaneity of process in terms of thermodynamic function. It is necessary to explain why the processes are spontaneous in terms of thermodynamic function, which will combine both the concept of enthalpy as well as concept of entropy. See it carefully. What I am telling, it is necessary to explain the spontaneous nature of a process on the basis of thermodynamic state function, which will include the concept of both enthalpy as well as entropy. Therefore, one more function is developed, and that is given by Gibbs and known as Gibbs-Helmholtz free energy. So let us see what is Gibbs-Helmholtz free energy. Gibbs free energy is given by equation G is equal to H minus Ts. Here we know that H is enthalpy and S is entropy at a constant temperature. Since H enthalpy is state function, temperature is state function, therefore entropy S is also a state function. So we know delta H will be equal to H2 minus H1. Delta T will be equal to T2 minus T1. And delta S is equal to S2 minus S1. Since enthalpy, temperature and entropy, all these are state functions, therefore Gibbs energy is also a state function and can be calculated by the equation delta G is equal to G2 minus G1. So let us consider G1 as Gibbs energy in initial state of system. By this equation it is written like this: H1 minus T1 S1. For final state G2 will be equal to H2 minus T2 S2. But since Gibbs free energy is studied at constant temperature and pressure, therefore T1 is equal to, see here, since we know the value of G1 in initial state of the system, value of G2 in the final state of system, delta G is nothing but G2 minus G1. Substituting the value of G2 and G1 from these two equations in the equation of delta G, what happened? Delta G is equal to G2, that is H2 minus T2 S2, minus G1 means minus G1 is H1 minus T1 S1. Solving that bracket, we can write delta G is equal to H2 minus T2 S2 minus H1, and then minus into minus plus T1 S1. This is plus T1 S1. Since the temperature is constant, T2 and T1 are same, let replaced by equal to T, this equation become delta G is equal to H2 minus TS2 minus H1 plus TS1. Now taking the similar terms on the same side, taking a similar terms together, we can write delta G is equal to H2 minus H1, H2 minus H1, then minus sign, this minus sign, in bracket TS2 minus TS1. See, this equation should be same as that of this equation. Is it right? H2 minus H1, that is correct, minus TS2 and here plus TS1. So TS2 here negative sign means minus Ts2 and minus into minus plus Ts1 it is there. So this equation is same as that of this equation. H2 minus H1 is nothing but delta H. So delta G will be equal to delta H minus Ts2 minus Ts1, that is T in bracket S2 minus S1, or the equation is delta G will be equal to delta H minus T delta S. This is the equation for gives free energy change for a chemical reaction depending on enthalpy change and entropy change of the reaction at a constant temperature. And using this equation one can identify all the spontaneous and non-spontaneous reactions very easily. Now let us see over here how the spontaneity can be identified on the basis of Gibbs energy change. That is relation between delta G and delta S total. We know this equation, delta S total will be equal to delta S of system plus delta S of surrounding. We are interested in the value of delta S of system. Therefore, we have studied the Gibbs free energy a state function in terms of thermodynamic state function. The spontaneity of reaction we have studied using a Gibbs free energy. If delta S of system is positive, we know easily we can come to know the reaction is spontaneous. But if this is negative, we must know the value of delta S of surrounding, and we are not interested in this value. Therefore, we have seen the Gibbs free energy. For this equation, if we consider delta S of system as a positive value, delta S of surrounding will have a negative value, because for the spontaneous process we should have delta S of system will be positive. So delta S total will be equal to delta S. I am dropping system. I am dropping here the word system plus delta S of surrounding. See here, if the system is not indicated, it is there as consider. You have to consider as a delta S of system. But for surrounding, it is always indicated. Delta S of surrounding should be always indicated. System may or may not be indicated. If it is not written as a system, consider that is the entropy change of a system. If this is positive, delta S of surrounding should be negative. So delta S of surrounding must be negative, that is minus Q reversible upon T, or that is equal to minus delta H upon T. So delta S of surrounding will be equal to minus delta H upon T. Substituting this value in this equation, we can write delta S total will be equal to delta S of system minus delta S of surrounding is delta H upon T. If we solve this, What we can write? Multiplying both sides by temperature T. So this side become T delta S total is equal to T delta S of 16 minus delta H. Temperature is cancelled. Both sides we have multiplied by T. This equation can also be written in this format. I am taking negative sign here. So left side become minus T delta S is equal to right side minus T delta S. This is the T delta S total. T delta S 16. This is minus. So this will be plus delta H, or we can write minus T delta S total will be equal to delta H minus T delta S. And just now we have studied the equation of Gibbs free energy delta G is equal to delta H minus T delta S. Let this is equation 1, let this is equation number 2. See, right side of equation 1 and right side of equation 2 are same, therefore their left sides are also same, and we can write delta G will be equal to minus T delta S total. This is important equation to identify the spontaneous nature of a process, spontaneous nature of a chemical reaction. If delta S total is positive, the reaction we know it is spontaneous. See what we have studied, delta S is equal to positive, spontaneous. If delta S negative means non-spontaneous. See that concept here. If delta S is positive plus at constant temperature, sign is minus. So delta S is positive means delta G will be negative for a spontaneous process. If delta S is negative, the process is non-spontaneous. Negative into negative, at that time delta G will be positive. That process is known as a non-spontaneous process. And now there is no any exception for a Gibbs free energy, and all the processes, whether they are spontaneous or non-spontaneous, can be explained with the help of Gibbs free energy, and their spontaneous nature can be explained. How the processes are spontaneous, how they are non-spontaneous, what are the different type of processes, what is equilibrium temperature, that part we will study in the, we will see it in the next lecture.